Hi everybody, welcome to my 19th axial bar video. In this video I'm going to be talking about elastoplastic analysis. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. Alright, so far we've been looking at situations where we assume that the E, Young's modulus for a material, is the same no matter how much stress we put on it. Alright, we put a stress of like 2000 megapascals, and then we assume that it has a corresponding strain. Then we'll go up to like 10,000 megapascals, and we assume it has a corresponding strain. But in reality, we know you can't do this, right? At a certain point, the material is going to fail. Alright? An elastoplastic analysis provides us with a method of sort of describing this sort of behavior. So let's just plot sigma versus strain. So stress versus strain. This is the same graph we used to find E. And for a material, E is going to be doing its linear region for a while. Then at a certain point, the material is going to fail, if you will. It's not going to snap, but also it's just going to like give up resisting. It's just going to like free spool out. Alright? And it's going to level off the graph straight like that. Okay? And this here we describe as the linear region, or let's go linear region. All right, or elastic region, right? Because if you stretch it in this region, it'll go back to this region. It's elastic. All right, if you stretch it outside of this region and you let it go to here and you let go, it's going to retreat back along the same slope as this here, but then of course you're going to have some permanent elongation there, some permanent strain. Alright, you can pull it up, let it stretch out, so it's just like pull, and all of a sudden just gives go and lets loose. You let go at some point during that time, it's just going to retreat back, and you're going to be left with a permanent strain. Alright, so of course this region here would be the elastoplastic region, or the elastoplastic. Okay, and we have some special words for what happens at this point here. Alright, so not specifically for this graph, but if you manage to plot a graph, let's use my trusty ruler here to make it look pretty, of the force versus displacement, so P versus delta, you'd find a similar sort of situation happening, right? And this piece here is delta plastic, alright? It's called the delta at the point that it goes into the plastic region is called delta plastic, and then the point, or the force at the point where this goes into the plastic region is called P with a subscript plastic, alright? So you can imagine for this sort of situation, you could find this behavior to happen in a straightforward sort of situation. You have a bar, you're pulling on it, P. At some point, bang, it's going to go into this region. But if you have something that's statistically indeterminate, alright, you can imagine something like this. You have a few wires. There we go. You're pulling down on this P. Not all these members are going to go into the elastic region at the same time, or the elastoplastic region, whatever you want to call it, the plastic region. Alright, we can think this one here is going to probably go first because it's carrying the majority of the load, and then these ones are going to go later. So if you would plot the graph of what's going on with P and delta in this situation, it would look slightly different. Alright, so initially you'd have the material just going. Alright, well this one's not in its plastic region yet. And then bang, it goes into its plastic region. Okay, so then it's going to kind of taper off like this, but it's not fully plastic yet because these ones are not in their plastic region. Then at some point those enter into their plastic region as well, and the whole thing tops off here. Alright, Now the corresponding places here, I got special names. So here we have delta plastic, P plastic, all right, the same as before. When the full thing is in plasticity, then we say at that point what that happens, we have a load P, that's the plastic load, and the displacement at that point is delta plastic. And here where it just starts to yield, all right, we'll use that word, with delta yield, P yield. So that's when your structure first starts to yield. And basically what most elastoplastic analysis problems are going to get you to do is to plot this graph. All right, now I've noticed in some books they use these funny words, ordinate and abscissa. Okay, I don't know why you would use these, but anyway, this is just code for X, Y. Okay. All right, so I kind of had a challenging time learning this, and when I was studying this, I kind of came up with my own like system to solve these problems. So here's my method. All right. So usually you'll be given the yield as a stress. All right. You'll be given at a certain stress, you'll just say delta yield. It'll go into the plastic region. All right. So the first thing you got to do is find the forces in all the members. All right, so going back to this example, I'll work through a detailed example of this axial example in the next video. So you find the forces in all the members. All right, that's not too hard. You do free body diagrams. All right, we've been doing that all along. Then you calculate the stresses. That's just the force divided by the area. All right, now the member with the greatest stress will yield first. All right, so that'll correspond to this piece here. Boom. All right, now most of the time the areas are the same, so you don't really need to do step 2, but you know, you might get a question where the areas are different. And it's the yield stress that counts, not the normal force in the bar. All right, and then you're probably not going to get like yield 1, yield 2, yield 3, yield 4, unless you know somebody's feeling really angry and they want to give you some hard time. But anyway, you can redo this process over and over. You know, find the first greatest stress, the second greatest stress, the third greatest stress, and you can potentially plot this graph with a bunch of different points. Another thing interesting to note is when the thing's in full plasticity, all right, when all of these members have failed, or not failed, it's gone to the plastic region, the same internal force is in every single one. And that makes sense, all right, because this P here is constant, so it's probable that the internal force will be constant as well. So that's just a fact you need to use. All right, and then you use the member that's just going into displacement to find the displacement. So in this case here, if you're plotting the displacement, in order to find the displacement, you find the displacement of this member that's just gone into displacement. Then you go back and you relate it to this one. All right, that might seem a little bit convoluted, but I found it tricky to calculate, you know, the displacement of this one because it's been in its elastic region for a while. So you'd have like an initial bit of displacement and then another bit of displacement. So it's best just to say, as soon as it goes into its plastic region, take the member that's just going into its plastic region and find the displacement of that member. And then you're going to have some relationship between these displacements, and you use that to find the displacement of the centerpiece. All right, which is usually what you're looking at, the displacement of the point of application of the load. All right, so that's pretty well my introduction to elastoplastic analysis. So a quick recap, you know, at some point in materials can't maintain this linear sort of region and they go into, I guess it's sort of a failure mode, but basically alternators like free spool where the stress in there remains constant but the elongation just keeps on happening. You know, at some point over here they're just going to like break, all right, but we don't worry about that in this course yet. And then we said for a statistically determinate problem, all right, we have a yield point and a fully plastic point. So if it's statistically determinate, this happens at the same point. All right, it yields and it's in its plastic region at the same time. But for statistical indeterminacy, you're going to have one member yield first, and then at some point later, all the members are going to be in plastic. And I went through my method of solving. I'll leave that up for a few minutes if you want to pause it and kind of digest it. All right, thanks so much, guys. I will see you in the next video, and we'll work through an example discussing elastoplastic analysis.